Now, next we'll be talking about the environment by which the microbes will thrive. Just to understand a little bit about the environment, moisture-wise, the highest nitrification rate we can achieve at what we call field capacity, or the amount of water in the soil that's held against the pull of gravity. Now, if we have excessive moisture, which is essentially leading to a lack of oxygen, that's going to impair microbial activity. And when we have the other extreme, when it's very dry and we don't have any moisture or very little moisture in the soil, that will also impair these microorganisms from their function in the nitrification process. Temperature-wise, if we have 75 to 95 degrees, that's an ideal range for temperature. And we kind of use temperature as a regulator for us in this nitrification process. So if we put on for example, anhydrous ammonia in the fall of the year, we use temperature in our favor so that we make the application when the temperatures are low and trending down, so we know the nitrification engine is slowing down, so that we hopefully will keep a lot of the nitrogen in the ammonium form going into the winter. Now, we can have higher temperatures when we put on our nitrogen, and temperature is not the cause of loss. All temperature does is actually drive the rate of nitrification, and once nitrogen is nitrified, goes from ammonium to nitrate, it's not lost. The way we lose nitrate nitrogen is by either leaching with soil water or by a process called denitrification, which we'll talk about both of those later on as two separate processes in the nitrogen cycle. Now, a little further on the microbial environment, from the standpoint of a favorable environment for activity, we need soil air. We discussed earlier that Nitrous amonis and Nitrobacter are both aerobic kind of bacteria. That means they need oxygen. Now, as a result, they're going to be inhibited by environments that have less oxygen, such as caused by soil compaction. So when we look at a standard soil that has a normal bulk density, it's not compacted, we usually think of a soil that's half solids and half pore space, and of half the pore space, half of that is filled with air. So essentially 25% of a soil volume of an acre furrow slice is soil air. The other is soil water, which is an ideal environment for microbial growth and development. Now, in order to favor microbes, specifically soil bacteria, we need to have a pH that's conducive to growth. So if we have an acidic environment, such as that in a soil with a low pH, then we're going to impair nitrification. The pH that favors the microbes responsible for nitrification, between 6 and 8. Now, when we think of that environment, let's just say, for example, we don't have oxygen. Let's say we put on anhydrous ammonia within about 7 to 10 days and it starts raining, and it rains for 2.5 weeks. Have we lost our nitrogen? Well, without oxygen, we don't have activity of nitrous amonis. And as a result of that saturated soil, as long as we don't have a lot of water moving through the profile, we actually have a stable form of nitrogen, which is ammonium. And no, it's not going to be lost through denitrification, and it's not going to be lost through leaching if it's a medium to heavy texture type soil. So what we have is a positively charged ion that's attracted to the soil surface, making it less likely to leach and impossible to denitrify. So that's kind of good, except for the fact that you have a saturated soil. When we look at how nitrification is affected by temperature, here you have a graph showing you time on the x-axis and nitrification on the y-axis. And let's just look at, if we have a temperature of the soil temperature of about 52 degrees, about 3 weeks after the nitrogen has been applied, we get a little over probably 23-24% of the nitrification process occurring. However, if we have a warm soil such as 75 degrees, we nearly have 100% of the nitrogen applied converted to nitrate within that same 3-week period. So temperature is a driver of the rate of nitrification. Now here's another graphic, and all this is showing that if we apply nitrogen in the southern part of the area shown on your map, and we check it May 25th of the following year, nearly 100% of the nitrogen applied November, December, or even March 15th had been converted from ammonium to nitrate. And that's without any kind of an enhancement, such as, in this particular case, a product called Inserve. Now, if we applied the enhancement, even when we applied the enhancement, a significant amount of the nitrogen is converted by May 25th into the nitrate form. Now, this is probably just one example of why in southern Illinois, or the southern part of the territory shown on your map, there is not very much, if any, nitrogen applied in the fall of the year, because regardless of the enhancements that we would use, it's a very good chance, or there's a high risk, of the nitrogen being converted to nitrates early in the next growing season, which makes it much more vulnerable to loss through leaching and denitrification.